Hello. So we have already visited the artificial neural network modeling approach that is inspired by how human brain works with the neurons and everything. And then in the previous video, we also discussed another modeling approach that is also inspired by how human brain works, which we refer to as probabilistic neural network. In this video, I will give a brief illustration on another approach that is also inspired by human brain that we call as fuzzy logic. Okay, I will start first with on discussing what fuzzy logic is, and then later on we will discuss on how to develop a model using fuzzy logic technique. Okay, I will start it first with what fuzzy logic is. When you we are using a Boolean logic, Boolean logic only consists of two values, 0 or 1. So it's only right or wrong, black or white, cold or hot, only two values to quantify an entity. That's what we do using Boolean logic, right? In contrast, fuzzy logic has a different approach. So if Boolean only have two values, 0 or 1, black or white, cold or hot, right or wrong, but fuzzy logic has varying number between 0 and 1. So it has a gradual number to represent or to quantify an entity. It's not like Boolean. As an illustration, probably you can see in this slide, if we are talking about temperature, when you are going to talk in Boolean language, if someone is asking you what is the temperature, then you will only answer it's cold, or the temperature is low, or it's hot, temperature is high. You can only answer it with these two values. That's how you do it if you are using Boolean language. But on the other hand, if you are going to answer it in fuzzy language, you have a gradual variable there. So you can say it's rather cold, it's rather hot, it's very hot, it's less hot, it's average. So you can say it in that range. For example, here, if you look at this diagram, if you are referring to a cold temperature, freezing temperature, then you can say the temperature is 100% cold and 0% hot. Or if you are referring to a boiling water temperature, you can say that the temperature is 100% hot and 0% cool. Or if you are talking about a normal body, human body temperature, 37%, referring to this diagram, then if someone is asking what is the normal body temperature, it's if we are going to answer it in fuzzy language, then you will answer it the normal body human body temperature is 50% hot and first 50% cool. That's how you respond it if you are going to use fuzzy language. Okay, having known how fuzzy variable works, later on in the last part of this discussion, then I will present to you how to develop a model of any system, just like what we did in the previous few videos when we were developing a model using artificial neural network, probabilistic neural network, naive Bayes. Basically, all of them are developing a model. So we can also develop a model which we will call it as a fuzzy inference system, or I will abbreviate it as FIS. But this FIS modeling technique, so it's same like other models that will take an input and then it will give an output. But this FIS modeling technique uses fuzzy variable. So the input that you will give to this model, you have to fuzzify it first. You have to translate it in fuzzy language. And then using the model that we develop, we can get the output. We can estimate the output, but of course the output of this model, because this model is developed based on fuzzy logic, the output is still in fuzzy language. So in order for us to understand what is the output, of course we have to translate it back to our language. So we have to defuzzify it. The model is just like any other model, it's just a model, but the model only takes fuzzy variables. That's why the input has to be translated in fuzzy language, and the output, in order for us to understand, to be able to interpret, then we have to translate it back to our language. Okay. The nice thing probably that I need to mention here, the model itself, the FIS model is pretty simple, very simple model. Sometimes you can also present the model in just a simple if-then rules technique. So it's very simple in terms of the modeling. The trickiest part probably is on how to fuzzify a variable and how to defuzzify it. Let's briefly discuss how to fuzzify a variable and later on how to defuzzify. Fuzzification is a process to translate our language. Well, since we are an engineer, so when I'm talking about our language, we always talk about number, right? Number is a language for engineers. So fuzzification, back again, fuzzification is a process to convert a number, a real number, a crisp number. So what I mean by crisp number is a real number to a fuzzy language. What you can see in here, this diagram, is to translate a temperature that is represented in centigrade, in degrees Celsius, to a fuzzy variable. So for instance, if you look at this diagram, this fuzzification process, I will rather call it as fuzzification process, same like in our previous illustration, in our previous two slides. This fuzzification process has two functions. Let's call it as a cold function and a hot function here. And then using these two functions, we can translate our crisp number to fuzzy language. So for instance, if I have a cold temperature, then in fuzzy language, I will say a cold temperature as 100 cold and 0% hot. If I have a very hot temperature, boiling water temperature, let's say, and then how I present it in fuzzy language, the hot temperature is equal to 100% hot and 0% cold, based on these two functions, cold function and hot function. Same thing also if I want to present 20 degrees Celsius in fuzzy language, it will be same like before. So if someone is asking me, what is the temperature today, or how cold is it today? If we are talking in our common language, my response will be just, it is cold, or I might just answer, it is 20 degrees Celsius, it is 20 centigrade. But if I'm talking in fuzzy language, If someone is asking me how cold is it, I will answer it by saying, well, the temperature now is 70% cold and 30% hot. That's how you will respond it if you will answer the question in fuzzy language. Okay. So how do we come up with this 70% cold and 30% hot for 20 degrees Celsius? Is based on these two functions that help us to falsify the crisp number there. So these two functions will help us to falsify the number there. These two functions that will need in falsification process is called as membership function. Number of the membership function in the falsification process is not necessarily only two. You might have more than two membership functions. Probably to represent temperature, you might not only have cold function and hot function, but you might also add one more warm function, for instance. So you have three membership functions. So you can add more membership function as you like to have a falsification process there. Okay, so that's how we falsify a crisp number, how we translate our language in terms of real scalar value to fuzzy language. Now, how about defalsification? Basically, defalsification is just the inverse of falsification, to convert fuzzy number to our language, to crisp value. There are many techniques to do that. We will discuss it in the next few slides. So some researchers, some scientists that offers different technique of defalsifications. One of the most popular defalsification technique is referred to Mamdani defalsification technique. But instead of talking about the defalsification technique alone using Mamdani, I will just present here in this slide. So what you are going to watch in this slide is how we process a variable using FIS model. So what I will present here is not only falsification and defalsification, but I will give an illustration also on how the model of FIS will look like. Okay, you still remember before when we have an FIS model, if you need to process the variable with this model, you have to falsify the input first. Once you process the variables using the model, you will get the output. The output is still in fuzzy language. You have to defalsify. So that's what we are going to discuss here. I will give an illustration of processing a variable using FIS model consisting these three steps: falsification, model evaluation, and then defalsification. The first step, let's start it with falsification. So what I'm going to do now, I have a model to give a quality of a restaurant. So if let's say I want to give a grade on a restaurant, whether the restaurant is good or not. How are we going to give a quality of restaurants? Typically, if you want to say if this restaurant is good or not, the easiest way is just looking at two factors: how the service in the restaurant, how the service is, and the second one is how the taste of the food, right? If the service is good but the taste is bad, then I will not give a high grade in that restaurant. Or the other way around also, if the taste of the food is great but the service is bad, it's lousy, it takes more time to deliver my order, then I will not give a high grade to the restaurant. Okay, but we are going to develop the model based on these two inputs. So we have an input of service and the taste of the food, and then the output will be the quality of the restaurant. And then how to define the quality based on the service and the taste of the food. We are going to use a FIS model. So the input here are service and taste of the food. Using FIS, we have to falsify these two inputs, the surface and the taste of the food. This is what I'm going to do. We will falsify the input first. I will start with the surface. So if I if I want to quantify the quality of the surface of the restaurants, the most straightforward way, probably I will give a scale from 1 to 10. If the surface is very good, they can deliver my order very fast. The waiters are nice and the restaurant is clean. I will probably give a grade of 10 for the service. Otherwise, then I will give grade of 1. So I will have a crisp scale for the surface input from 1 to 10. But this is not what FIS wants as an input, but FIS needs a fuzzy language. So I will fuzzify this surface scale from 1 to 10 to fuzzy language. How will I do that? I will use membership function. So I will have first membership function, the poor membership function to represent a poor surface. And then I will use good membership function and excellent membership function. So in contrast to the illustration of the temperature in the previous slide, in fuzzifying the surface grid, I will use 3 membership functions here. You don't need to have the same type of functions for the membership function. As you see here, for poor and excellent, I use sigmoid-like functions. But for good function, I have I don't know what you call this. It's like a normal distribution function, or I don't know, any other kind of. You can name anything for this kind of function. But the bottom line here, you don't need to have exactly the same type of function to represent the membership function. Okay. So I will use these 3 membership functions to falsify the surface grid. I have another input also, the taste of the food. Okay, so same thing. Normally in our language, in our crisp language, in our real scalar value language, I will grade the taste of the food from 1 to 10. But then if you want to translate it to fuzzy language, then I need membership function. So in here, I use 3 membership functions to falsify the taste of the food here. Rancid function, fresh function, and delicious function here. As you can see here, I use different membership functions compared to the surface falsification process there. So you are free to use any function. So with these 2 falsification processes, I can falsify the surface input and food taste input. And then the last one is the output, the quality of the restaurants. Of course, for this, I need to define a falsification process also. That later on, I will need it to defalsify the output. So same thing then, here I will use 3 membership functions. As you can see here, I use triangle function for the membership function of the quality of the restaurant. And I have also three membership functions: bad, mediocre, and great. Okay, so we have already finished to construct the falsification processes to translate the inputs and output. In particular, for the output, we define it now, but we will use this later on in the defalsification process. Now the model. After we falsify the input, we can process the input in fuzzy language to process it in the model, in the FIS model. The FIS model is very simple. It doesn't have to be like this, but this to illustrate one of the most simple FIS model. The simplest FIS model is by using if-then rule technique. So because I have three membership functions for each of them, I will have three if-then rules to develop the FIS model. The first if-then rule is to correlate the first membership function, the poor, rancid, and bad. So if the service is poor and the food is rancid, then the quality is bad. The second rule will correlate the second membership functions. If the service is good, the food is fresh, then the quality of the restaurant will be mediocre. The last one, if the service is excellent, the food is delicious, then the restaurant is having a great quality. Okay. So using this rule, we can get the output of the quality of the restaurant, but still in fuzzy language. Let's take an example now. For instance, for the service of one particular restaurant, in my language, I will give a grade of 3. This restaurant, the service is not that good, well, slightly good, rather poor, but not excellent. So I will give a scale of 3 for the service. And the food taste, not that good also, so I will give a grade of 3. So the value of 3 for surface and the value of 3 for the food taste is in my language, in our language, in our crisp language. But to process it using FIS model doesn't understand this crisp value. He doesn't understand what 3 is for surface, what 3 is for the food taste. FIS doesn't understand them. So we need to translate it to fuzzy language. So in that case, then, for surface with a grade of 3, the scale in the poor membership function is 30%. For grade of 3, for food taste, in rancid membership function, it will be equal to 45%. So we are talking now about the first membership function. The value of the membership function for surface when I give a grade of 3 is 30%. The value of rancid membership function when I give a grade for a food taste of 3 will be equal to 45%. And then the FIS model say, because now we are referring to the first membership functions, poor and rancid, if you look at the first if-then rule here, if surface is poor and food is rancid, and then the quality will be bad. So if I look at this, the poor surface is 30%. The rancid food taste is 45%. If I take n logic between 30% and 45%, so what will happen? N values mean both of them has to have the same value, right? That's how N logic works, isn't it? 0 and 1 is 0, 1 and 0 is 0, 0 and 0 is 0. Only 1 and 1 that will give an output of 1. So now I have 30% and 45%. So what is the output of this N process? The output of the 30% and 45% will be just the overlap between 30 and 45, which is 30. It's the minimum. 30% is the overlap between 30% and 45%. So if you are using N function and logic in your if-then rule, then what you have to do, you have to take the minimum amount. The if-then rule in your FIS model is not only limited to AND logic, you can also have OR logic. So in here, if you have OR logic, then 30 or 45, the output will be 45. But in this case, just for illustration, I will use AND logic in my if-then rule process here. Okay. So for the first membership functions, I have already processed it. 30% poor and 45% rancid will result in 30% bad. Now I have to evaluate it for the second membership function. If service is good and food is fresh, then quality is mediocre. I will take a look again here for a grade of 3 for the service of that restaurant. The grade is 3. If I look at the scale on the good membership function, apparently it's equal to 70%. And for food taste of grade 3, if I look at the fresh membership function, it will be somewhere here. The value apparently it's 80%. So I will evaluate it again with this if-then rule process. If surface is 70% good and food is 80% fresh, then the quality will be 70% mediocre, right? It's an AND process then here. So you are taking the minimum 70 and 80, it will be 70. Right? Now we move to the third membership functions. Excellent for service and delicious for food taste. For grade of 3 in service, the excellent value will be 0. So I get 0 for the excellent. For food taste of grade 3, the delicious scale will also 0% there. So for as an output then 0 excellent and 0% delicious, the quality of the restaurant is 0% great. Okay, so this will be my output of the model. But the output that you see here, the one that I put in hash area there, this is still in fuzzy language. To us as a human, we don't understand what does this mean. If to me this value is given, I don't understand by looking at this figure what is the quality of the restaurant. So what we have to do now, we have to defuzzify this fuzzy variable in the quality. How to defuzify? There are a lot of techniques to defuzify. The simplest one is by looking at this area and the quality here. I have an overlapping area there. Now I indicate it in gray. So how to translate this back in the crisp value? Among many techniques, the simplest one is by taking the centroid of the area, centroid of this gray area. So let's say if the centroid is here, then I can say that the quality will be somewhere here. If I'm looking at the diagram, if I'm looking at the function there, at the plot there, apparently the quality is 45. So this is how fuzzy model will process the input and output to get the output. In this example, that means if the surface is 3, the food taste has a grade of 3, then the quality of the restaurant is 45. Okay, so this will give an illustration how FIS model works. The centroid of the area for the diversification technique is not the only approach. You can also use bisector area, where to diversify the fuzzy language, if you are using bisector of area, the crisp line will partition the region into 2 regions with the same area. So you have the area, the gray area, you just split it into 2 regions with the same area. The splitting point, that is your diversified value. You can also use min of max. So if you have this fuzzy variable again as the output of your restaurant quality, if you are using min of max, you just take the mean value. So you just take the mean value of the maximum portion. So the maximum portion is here. This is the highest value. You just take the middle of it, and this value that is represented by this line is our diversified variable, the crisp variable of the output. You can also use smallest of max. So from this maximum portion, you just take the least, the leftmost value of this maximum portion to diversify the fuzzy variable there. You can also use largest of max. It's just the opposite of smallest of max. You just look at the maximum portion here and then take the rightmost point of the maximum portion to diversify the fuzzy variable there. So you are free to use any of these. You might have a question which one then that I should use. There are many approaches, there are many techniques, there are many ways to do that. You are the engineers, you are the designer, so you are the one who is responsible to define the techniques. It's your choice, it's your subjective assessment, so you are free to take anything based on your subjective measure. Okay, so the defuzzification technique that we discussed before is referred to Mamdani FIS model, where the output of the FIS model is evaluated based on the area of this output membership functions, right? That's what we did before. But there is also another approach that is called as Sugeno fuzzy inference model, or sometimes is referred to as Takagi Sugeno. It's named after one Japanese scientist there. Instead of using this pictorial approach to get the output, Sugeno uses function. So this is what Sugeno does to get the output of this model. The model is still using if-then rule approach, but this is what Sugeno did. So he used a linear function that use the first input and second input. So in here, x1 can refer to the surface grade. In our previous example, it's 3, and x2 refers to the food taste grade. Again, by coincidence, in our previous example, the second input is also 3 here, with a certain proportion of coefficient p and q here. So using this function, you can define an output for each membership function. So let's say for the first rule, referring to the first membership function, if surface is poor, surface x1 is poor, and the food taste x2 is rancid, then the quality y1 will follow a certain linear function pi x1 plus p1 x2. Sorry, so it will follow p1 x1 plus q1 x2. In this case, in our first rule here, referring to the first membership function, the p1 is 2, the q1 is 4/3. For the second rule, we are referring to the second membership functions. If surface x1 is good and food taste is fresh, then the quality will follow this linear function, a combination of x1 and x2. But we have different coefficient here. P2 is 8 and Q2 in our case here is 12. For the third if-then rule, if the surface x1 is excellent and the food taste x2 is delicious, then I will use this another linear function, where in our case here p3 is 32 and q3 is 180. Okay, so in Sugeno FIS, we are not going to find the area of the output membership functions and then defacify it with, I don't know, either centroid of area, smallest of max, maximum of max, or any other techniques like that, but we are just simply use that equations. Okay, so how to defacify it once you define all of this equation? Let's say again, same thing like before, the fuzzy value of surface 3 for poor membership function is 30%, let's say. And then the fuzzy value of the food taste for rancid membership function is 45%, like before. If we are still using the AND logic between first input and second input, so the output will be 30%. So this will be the lowest one, will be the dominant. And then we have a scale here that is taking the minimum of the AND relationship between the surface membership function and the food taste membership function. Because we use AND function, then the output will be 0.3, 0.3, and 0.45 is 0.3. So alpha will be 0.3 in this case. In that case, then the output of y1, you calculate it, it will be equal to 1/3 times 6 times 3, x1 is 3, x2 is 3, so y1 will be 10. Similarly, for the second output will be, just to follow this function, the output will be 60. For the output of the 3 rule will be 420, following the green function here. And then by looking at the output of the if-then rule, where from the first rule, if the surface is 30% poor and the food taste is 45% rancid, then the alpha 1 will be 0.3, so it will be 30%, taking the minimum. And then for the second rule, if the surface is 70% good and the food taste is 80% fresh, then the output alpha 2 will be 70%, taking the minimum again. And then the last one will be 0. So to translate the output, to diversify the output, we just take the proportion of this. Alpha 1 is 30%, 0.3. 0.3 times 10 plus 70% times 60 plus 0 times 420. It will be equal to 45 in this case. So, and then of course you have to normalize it with this, right? So this is how diversification process will take place using this Sugeno FIS model. The diversification will be carried out by a function. How to define this function, how to define the coefficients, it's up to you to decide. It's up to you to define, because you are the one who will design the model. Okay, so yeah, this concludes how FIS model works. Now I have 2 more slides to present to you one type of modeling approach, because up to now probably you still have a question how to optimize all of the parameters. I can design my own model with my own subjective measure, so I can define all of this membership function with my own interest. But how if I want to use this model to capture a certain behavior, a certain system, a certain function? That means then I have to tune the membership function. I have to tune the coefficient in my Sugeno diversification technique. I have to tune the membership function in my Mamdani diversification techniques, right? I have to tune it properly to be able to capture a behavior of a function. If you are only purely using FIS, you cannot do that. You have to do some trials and error. But there is one technique that is based on neural network, how human brain works, that is called as an ANFIS, Adaptive Neuro-Fuzzy Inference System. So as it implies by its name, the fuzzy inference system here, the FIS, will be adaptive. So to model this ANFIS, more or less look like the artificial neural network, but it's different than ANN here. In ANFIS, we have a fixed number of layers. It's more like a probabilistic neural network, more like PNN in here. But it's different in the approach here. For ANFIS, we have fixed number of layers. We have 4 layers always. The first layer represents the membership function. So okay, I didn't count for the very first layer. Normally we count the input as the first layer. The input is just an input, so in here I don't count it as a layer. In here the first layer is just a membership function of each of the input. And then in the second layer, we multiply the output of the membership functions. In the third layer, we normalize the output of the second layer. In the fourth layer is the defuzzification part. We defuzify the output from the third layer to get into the input in the very last layer of the output layer there. How it works, I will give a brief description in the next slide here. The first layer. So the first layer basically is to evaluate the output of each membership function. So in here for illustration, I have two membership functions for each of the input here. So let's call the first membership function for the first input as mu A1. The second membership function from the first input is mu A2. So A here corresponds to the first input in here. Similarly, the next two membership functions are mu B1 and mu B2 there. But basically, the output of this layer is the output of the membership function. In our example of quality of restaurants, then it will just simply 30% poor service quality, or what was it before, 70% good service quality, or 45% rancid food taste, something like that. So it's just the output of the membership function. And then the second layer, if we take the analogy of our restaurant quality before, where to model it, we use if-then rule function there. In this end phase, it doesn't use if-then rule function, but it multiplies the output of the first membership function from the first input and the output of the first membership function from the second input. In our illustration of the restaurant quality case, we take the first two membership function of the first input and the second input. And then in the second if-then rule process, we take the AND logic between the output of the second membership function from the first input and the second membership function from the second input, and process it with AND logic function. That's what we did in restaurant quality case before. But in AND phase, we don't use if-then rule, but we just simply multiply. And then the output of this layer, then it will be just simply multiplication of these two membership functions. So the output of this node, the W1 here, is just the multiplication of this output, the mu A1 and mu B1. The output of the second node in the second layer here is just the multiplication of mu A2 and mu B2. Okay. Now we move to the layer 3. What it does in layer 3. Layer 3 is nothing more, just normalization of these two output in the second layer. We sum it, you normalize it. And then the last layer, we multiply the output of the third layer with a certain function, fi. Okay, so the output of the first node in layer 4 is just f1 times the output of the first node in the layer 3, w1 bar, and the output of the second node in layer 4 is just W2 bar times F2 here. And then the final output will be just the mode. Okay. So somehow if I look at this, we have few parameters to be tuned in this FIS. The membership functions, all of these membership functions have to be tuned in this ANFIS. F1 and F2 are also unknown, so these are the two functions that have to be tuned in this ANFIS. The two middle layers, layer 2 and layer 3, are fixed layers, so you don't have to tune anything. So it's a fix, totally fixed. You don't have to add the layer. There is no such thing called a hidden layer like in and it's fixed. The number of layer is fixed, and there is no parameter to be tuned there. The parameters that we are going to tune in this ANFIS is only the membership functions parameters and the F1 and F2. But in this discussion, I'm not going to discuss with you on how the tuning of these parameters will take place. I will just only present how ANFIS actually works. One more thing that I have to mention there, that I can mention, if you look at this ANFIS structure, basically, if I want to correlate it with the traditional FIS model, the first layer is nothing more, just a falsification step. The two next layers, layer 2 and layer 3, is nothing more, is the modeling process. In our restaurant quality example, the modeling uses if-then rule, but in ANFIS here, the modeling uses algebraic operation, multiplication of the membership function, and then normalization of the output of the second layer. So layer 2 and layer 3, I can say if I take the analogy to the traditional FIS is the modeling part, and then the last layer, layer 4, is the defalsification step. Okay, so that's how we can see from this ANFIS structure. So that slide concludes our discussion, our sharing story about ANFIS, the last model that I can share in this course. This slide will also conclude the end of this course. So hopefully you gain something. Hopefully I made everything clear. But anyhow, if you still have some doubts, you have some question, please feel free. Don't hesitate to send me an email, or you can also drop me a call to my office number. Okay, thank you so much, and see you in the next occasion.